All right, sorry. Good morning, everyone. Suppose good evening in some of your regions. Welcome to Math Finance 2. First, just mic check. Can everyone hear me all right? Just type in something. Okay, thanks. You don't have to raise hand yeah. Okay, cool. Just type in. Yeah, that's fine. Talk to the mic. Okay. All right. So I suppose we have met at least at the orientation. So I'm Triad. I'm the acting director for the program. So I'll be. Oh yeah, no problem. I'll be your instructor, right, for the course. So first, right, kind of like the way I want to conduct the lecture is pretty open. Like if there's any time you have any questions, anything, feel free to type into the chat or, talking to the mic, okay? I prefer you ask questions and I clarify for you right away rather than waiting to ask the questions later. It's 3 hours and so it's pretty long. So we'll take a break of 5-10 minutes in between. Whenever I feel like a good time to kind of take a break, I'll let you know. All right. So we won't run for like a 3-hour stretch, but we'll take like a 5-10 minutes in between. What else? So about the class, right? About the class. So the syllabus has been posted. OK, so please read the syllabus on the Canvas. It basically just routine stuff about information. Your TA, you have worked with him before, review session, course. So yeah, so let me say something first. All right. So I don't know. There are many things I want to say about the course. So of course it's Math 622. Math Finance 2. So several things. And maybe I want to say this first, that the way I want to run the class, right, is so far, right, in Math Finance 1, you have learned, so let me say this, right, in Math Finance 1, basically Professor Larson, I believe, has done a great job teaching you the probabilistic background, the discrete model, namely the binomial models, for the so-called security market, the fixed income market, and the foreign exchange market. Okay. So in Math Finance 2, we'll continue with that. So let me say, right, discrete model. All right. For fixing for security, right? Security option, fixed income, and FX, okay, foreign exchange. So in Math Finance 2, we'll continue the journey. Actually, I like the setup of this Math Finance 1. It kind of gives you an overview of what the math or what the topics should be. So it kind of break it down to 3 sectors, right? In Math Finance 2, we do the same kind of group, same sectors, but we'll do with continuous model. And by continuous, right, I guess we mean continuous time, right? Discrete, there was discrete time. Continuous time model, namely the Black-Scholes model. And the main tool, right, the main kind of buzzword is Brownian motion. Okay. So that's the topic. So that's the goal for the course. In terms of text, this gets a little tricky. All right. The official text for the course is, of course, Shreve, right? Whatever, I forgot the name already. You probably have used it a little bit in the first course, Shreve 2. Okay. I think Brownian motion and something in continuous time. But that text is pretty challenging. So I encourage you to take a look at it, and then peruse it, just to get an idea of what the topic is about. But right, a lot of the time, the content in terms of math I'll try to deliver to you is from the lecture and lecture notes. So pay, very careful attention to the lecture to see if you can get everything you need. All right. Otherwise, like, looking for your own information may be a little bit challenging. On the other hand, these are pretty standard knowledge these days, so you can Google them. But again, right, Googling requires some kind of know-how. So if you don't know how to Google, you may not be able to find what you're looking for. But so basically, I'll try to deliver the math content, right, on my own from the lecture notes. So that's why attending the lecture, I think, is pretty important. On the other hand, I want to mention this one, all right, whole, options, futures, and other derivatives. Okay, so this one is very well known, and it's actually I think it's used in some business schools or that kind of thing when they teach a course like, quantitative finance. The reason is Hall, right? He's a professor at I think U of Toronto, is very, very well known, right? And this text does a great job in balancing between the, well, actually, it is very light on the math, but it does very good job of explaining the finance, the background, the kind of the applications in what we're doing, okay? In this kind of like, pricing activities and beyond. So the book is larger than life, meaning there's a lot of information, but it used to be, and I think it may still be the case, that students who want to go to industry or who goes for interview, right, kind of read these books to find out more information for their interview. So I highly recommend, right, that you, I think obtaining a copy is not that hard these days. Take a look once in a while, all right, as we go through topics, and just see what he discusses. I will quote from the book, or the way I discuss the lecture is influenced by this book as well. So definitely, right, check out this book. Very, very important. But again, right, the way I want to deliver the lecture is self-contained, and you are strongly encouraged, okay, to read more on your own, because you're at a graduate level class, and self-study, all right, self-education is a very important part of what you should do. So text, right, that get any text you want, okay? Read, these are the two recommended ones, but read more on your own, all right? And if there's any kind of questions you have, any discussion at any time you want, feel free to send me a question. In terms of, I don't know, right, philosophy or something, okay? Meaning how I want to run the course. I want to, and don't take this, like kind of in any kind of extreme way, but I want to make it light on the math, but focus on the application. All right. This doesn't mean that it's going to be easy. All right. I know that, I guess a lot of you are, not very fond of the math, and you would love applications, but I completely agree with that, because right, you eventually, hopefully, a lot of you want to get jobs in industry, so you want to see how these things are used, what contexts are used for. On the other hand, I want to caution you, and the reason why I want to focus on the applications is applying things correctly, meaningfully, okay, is definitely not easy. You need good thinking to do so. And one of the prerequisites actually is at least a decent background in mathematics. And for that reason, right, I think Professor Larson did, again, right, a fantastic job preparing you to do so. So I don't have to work as hard, right, on your math. I can, be a little more free in terms of like guiding you into the applications. Okay, so but what do I mean by that? All right. So the way I view these topics, okay, math finance, it has three components, and I think you have heard of that, or seen that elsewhere. The three components, when we think of them, quant finance activities, okay, at least according to me, is like this. There's the math slash modeling part. There's a finance part, and there's the stat part. I mean, I'll throw in the buzzword data science here, okay? There's nothing data science that we're going to discuss here, mostly statistics, but statistics always deal with data. So I guess might as well drag in data, not data science exactly, but might as well throw it in. So what are these different things? So to give you an illustration, and we'll keep doing this, all right, over and over again. So math modeling is, for example, come up with a binomial model for the underlying. Be it the stock, the interest rate, or the foreign exchange. Now, right, people tend to underestimate the math modeling aspect of these components. And this is where, right, our program tends to focus more on that. The reason, right, just because something is a binomial model doesn't mean you know how to work with it mathematically. Doesn't mean you understand, right, the mechanism behind it, right? So it's very important that people get a good hold on the model, right? But then on the other hand, I think, right, overemphasizing on this is probably not balanced either, because there are these two components right here that, for example, if you go to a business school, you overemphasize on the finance, and you go to a stat program, you overemphasize on the stat, maybe, okay? But what's the finance side, for example? All right, the finance side are questions that would be pretty surprising to you that I like to call them financial argument, or questions that you might hear a lot on interviews, that basically they don't like you to drag in the math to explain stuff. They just want you to say, oh, intuitively, why does this work? Intuitively, why does something work this way? So let me just say something like this, okay? Demonstrate by a question rather than explaining more clearly what the financial aspect is. But for example, why is American call, or let me say this, why is American option always higher than European option? Okay, I think this is easy. And I think, right, when you think of the reason for this, okay, you would hopefully not explain it mathematically, right? You would explain it financially. But a less trivial question that would require financial, or would encourage financial argument is this: why is American call equals to European call in price? Okay. Now we'll get back to this question today, but I like to ask, or I like to see, right, if just give me a response in chat or something. How many of you know this fact or think that this fact is very well known? How many of you can explain it in an obvious way? Okay, Kashif, you know the fact, or you know the reasoning for the fact?
Hi, Professor Pham. Uh, this is Kashif.
Go ahead. What? So yeah.
The fact that I know of is like American option gives you more choices, so you can close your option at any period of time after the defined period of time.
All right. So that explains this, right? That is no less than Europe option. That's right. That's the financial reason. But for the American call equal, right? It's not strictly greater. It's equal for the call option. Do you know this fact, and you know the reason why?
No, Professor.
Yeah. No, it's fine, right? I want to bring this up. But do you know that American call is equal to European call?
It can be. That's what I.
Not can be. It is always.
It, is it
Yeah.
always?
Yes. Yes. Yeah. Right.
But
So
wouldn't American call have more more choices?
exactly. That's why it's surprising. But that's why people would love to say you come out of a math finance program, whatever. They say, what do you think about these two? And if you say it can be greater, then I think that's the wrong answer on an interview because they expect you to know more. It's always equal. Yes. Yeah. It's surprising, but it is. All right. Now again, right? I bring in these facts because, right? Um, they tend to right revolve around right and exactly if you just think about the math it's really complicated to even try to figure out why but the financial argument right bring out the reason okay so the financial intuition is something we don't want to miss all right I think you haven't heard of the Greeks yet right the Greeks because I think that's part of the continuous time model. Does anyone have any? Did everyone hear of the Greeks? Delta, gamma, rho, that kind of thing. Vega, not the Greek people. All right, two. All right, only two. Okay, that's
I've heard those terms before. Yeah.
okay. Yeah, right. But the Greeks, when people bring it up in an interview question, right? Again, they don't want you to hear some sort of like formulas. They want to oh, that's fine. You can speak. All right. Or take your time. Um, they want to hear the intuition. All right. For example, why is like the delta of the call option always between 0 and 1? Why is it always positive? That kind of thing, right? Um, or yeah, maybe they will ask you why is the Vega always positive? Can you explain it intuitively? Something like that. All right. Now, I'm not trying to say, all right, by advertising these facts, I'm not trying to say that I'm an expert, okay, on these things either. I'm aware of them and I'm deeply aware of them or I appreciate them, right? But I just want to bring it to the discussion or I want you to pay attention to this, all right, in preparation for right your journey ahead. And I will try my best to bring out right these kind of questions. I want to include these questions into evaluation. All right, not just the math. So I hope I'm the expert on this part, right, the math part. But the other ones I will do my best to illustrate them. But our class activities will focus on them too. So the stat part, right? What about the stat part? So the stat part, there are many aspects. Okay, I just want to mention a very simple aspect, which is model calibration. Okay, very simple. Oh, and maybe let me throw in stat data science. I think there's a comp sci always staying behind it or code. Okay, not super bad, right? And I think you know what it means. So, for example, right in the binomial model, how many parameters does a binomial model depend on? I mean, roughly. Yeah. Uh, uh, three. So which three, Kashif?
So, Professor, up and down probability and the starting point.
Okay, S0, right? So up, down, let's say, okay, UD S0. Actually, there could be, you can throw in R2, right? But so S0 is current stock price. How would you find U and D? How would you find U and D? I know, right? In a math problem, U and D are given to you. Now, if you go out to work and say your boss asks you to use the binomial model, blah, 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 where does U and D come from? Unless, I mean, except when he already give to you, where does U and D come from? Okay, observing, but observing where? And okay, all right, but right? But so that just says that, right? This is a statistical activity, right? So you need to collect the stock price, okay? You need to run something, you need to run some procedure so that you get some estimator, right? Now, again, right, these are not things that we should focus on in this class. On the other hand, I feel like, right, mentioning only because mentioning these models and not getting into these aspects, right, would kind of, I don't know how to say this, not do a complete picture for you. And so we will, again, right, attempt these activities. I will ask you questions that involve coding, collecting data, that kind of thing, all right? Those will fall more into extra credit because, again, I am aware this is a math class. So your exam, okay, will be just the mathematical content, but you have plenty of opportunities, okay, to earn extra credit doing this kind of activity, okay? And this will just be part of discussion, maybe. I don't know how to give credit, right, for financial argument, but okay. So it's just my philosophy or my flavor that I want to, okay, orient the class in these two aspects, as well as, discussing, right, the modeling aspect. And by modeling, I just want you to understand the model, okay? I don't necessarily require you to go super deep into the math, but you must know enough math to operate with the model, okay? Any questions? All right, so now let's, so to start, okay? So to start, like today, let me just do a soft review, right? Of, so, okay, so the plan is this, okay? And so don't trust the schedule that I put on the syllabus, all right? That just copy and paste from the previous iterations I taught the class. The actual things that we do will probably deviate from that a lot. So again, right, pay attention to the lecture, or if you're not very aware what topic I'm discussing, please just ask. So, but the plan, right, the big plan for the whole course is we're gonna do wanna do option first, okay? And then I think we'll go to probably FX, and then we'll do fixed income. I might swap this too. I don't know, okay? But so by that I mean, right, talk about these products under the continuous time model, but also I will not neglect the discrete time model, okay? We'll go back and review that a little bit, because the whole point of discrete time model, trust me, is that it's super easy to understand what's going on, okay? When it goes to continuous time, the intuition kind of falls down a little bit. And so a lot of finance, a lot of like intuition is built up in the discrete time model. So, I hopefully I can, most of the time I will start discussion with a brief review of discrete time model, and then throw in whatever aspects I think is relevant, and then we'll go to continuous time, okay? So we will start with option, okay? And so okay, what do I want to say here, right? So first, right, there's a name, right, that basically the universal name for all this activity we do is called derivative pricing, right? So this actually does not just apply to option. It applies to FX, it applies to fixed income, etc., right? So derivative pricing applies to everything. So first of all, right, why is it universal? So the name derivatives mean what, right? So I think people usually say derivatives, they could say options too. So derivatives, right, I hope you have seen it before. It just means some kind of asset, right, whose value depends on some underlying. Right. So basically it's an asset not necessarily have an intrinsic value in and of itself. It does, right? It does have a value, but its value is kind of like a function, right, of something, some other thing. So for example, right, that a call option, right, depends on, oh, so the word depends, right, also means derives, right, comes from. So that's why it's derivatives. It has nothing to do with differentiation, right, in calculus. It comes from, right, some other stuff. So options, right, depends on stock, right, on security. You know, let's say swaption, right, or like cap and floor, right, depends on interest rate. And so maybe this is stock call option, right? Because you can also probably have some kind of FX call option, right? And so this, of course, depends on the foreign exchange rate. Okay, so it probably is very simple, but the first thing you want to do is you must be aware of what it is that you are modeling. Okay, so when it comes to model, you always model the underlying, whatever that is. Meaning you give a fundamental stochastic model for it. You describe how it behaves. And the pricing, right? So, and the pricing activity is basically price the derivative based on the underlying, okay? Because basically when you say depends on, mathematically, that means it's a function of, right? It's a function of. So if you say, right, for example, let's say the underlying is ST, then the derivatives that you talk about is a function of ST. So V, right, V call, basically you're saying is some kind of function of T and ST. Okay, your pricing activity is to figure out what this function is, to figure out what this F is. Okay, to figure out, right, what F is, what this relationship is. Is that okay? So, right, pricing is not about modeling, right? Pricing is not about modeling of the derivative. Okay, that's important. That's where the math comes from. I mean, the math comes from in many places, right? But the model activity is on the underlying. Like you model the stock, you model the interest rate, you model the exchange rate. And then from there, right, you use your math, you use your risk neutral framework to do the pricing, meaning you try to figure out, okay, what is the function relation? What's the functional relation between the underlying and the derivative? Is that okay? So now, so let's ask an obvious question here. Why do we do pricing? In other words, what value does it give? You know, you are learning some activity, right? And I guess the hope is that you can go and sell your service to someone, right, who pays you money to do so. And they probably, right, in all fairness, can ask you, why do I need to pay you to do this? What is your answer? To make it concrete, right? For example, let's say I have Google stock. Okay. Everyone can observe what Google stock price is right now. Let's say I have call option on Google. Let's say expiration, I don't know, let's say March, okay, 1st, 2021. Let's say strike, I don't know, 9:50 I don't know what Google stock price is now. Is it still 1,000 or more? Okay, but anyway, let's say 950. What's the call option price right now? Suppose I want to know that price of this. What do you suggest I do? Is the question clear? It's not a hard question, by the way. I'm not asking for a payoff function, Kashif. I'm asking for its price. No answer? Well, the answer is actually very simple. Look up on Yahoo Finance, I don't know, or Bloomberg or whatever. Isn't it? You are aware that these options are posted, the price are posted on Yahoo Finance and Bloomberg and these kind of places, right? Yes, no, too obvious. But then, so why do you do pricing then? I can look up stuff. I can see it. Why do you do pricing? So maybe let me ask you this. How many of you believe that there's some secret employee of Google somewhere running some model like binomial model like you learned, and then, you know, or employee of Yahoo, I don't know, right? And then kind of post these things on the Yahoo Finance for you to see. So, right, the Yahoo Finance gives some price. So do Yahoo employ a bunch of, like, you know, poor graduate students like you running some binomial models in the background and output this query for the customers? Is that how this works? So where does the Yahoo Finance price come from?
The exchange, like NYSE or?
Yeah, the Yahoo Finance price exactly comes from the market, comes from trading, right? So this just exactly report trading, right? This comes from the market price. So buying and selling. So correct. So then again, so you learn all this pricing technique, that kind of stuff. What is it that you're using? Because if I don't want to know the price, I just look up. Why do we do pricing? Okay, so if you were to do your fantastic pricing activity and you found that the call option is underpriced, you would go ahead and buy the call option right now, hoping to get rich right away. If that's the case, then I think we should all do it, and then we should quit, you know, going to school right now, right? We can all be rich pretty soon, isn't it? So you can find out if the price is overvalued, undervalued, or rightly priced using some model. Is that what you believe? Well, all right. So let me save you the suspense. I don't think so. Okay. The activity of pricing, meaning like the activity of modeling this kind of thing, is never to figure out what the price is. Okay. It's not the point. And exactly, I think a lot of misconception is that we do this to somehow be the god of the market, or to, you know something the market doesn't. Okay, so pricing is, surprisingly enough, okay, by pricing I mean these activities, it's not about finding prices of options. Okay, at least most of the time. I'll explain the exceptions. Most of the time, right, you accept the price of the market as given is correct. Okay, you don't question it. The market has already done its part to balance all the supply and demand to tell you what the right price is. Okay, so the modeling activity, okay, is this, or the value of your pricing activity is this, that when you do pricing, okay, pay attention. So when you do pricing, right, so you're saying that the price of the call option is a function of, right, let's say, and let me just do 0, okay? So if it's 0, then it's just a function of the current stock price, the current underlying price, that's clear. But beyond that, it's a function of whatever parameters that you throw in to the model. For example, U, D, R. Okay, I hope that much is clear. In other words, right, that depend on how you plug in the U, you plug in the D, right, you plug in the R, you get different output. Yes, for the option price. That's the whole point of function. But okay, you in the, so this is the math, okay, this is the model. In other words, you accept these as given, and this is output. So this is input, and this is output. Okay. Realistically, the way you use it, the way you get paid on a company, in a company, is that you accept the market price as input. So let me call it V call market. Okay. So meaning like, you know, every employee would have access to a Bloomberg station. All right. I guess Yahoo Finance is not sophisticated enough, but will have access to something that would tell them right away what the market price is. Okay. So then what is the output? The output that you want, okay, that is a consequence of your pricing activity, is something like, I would just call maybe U hat, D hat, meaning estimator of U and D, right, based on the market price. Okay. And so whenever you do this, right, the value you get out of this in terms of finance parlance, they usually call it implied value. Okay. Meaning it's implied from the market price. The market price implies that currently the U is this, the D is this. Okay. But here's another step, right, toward like the finance. In real life, people don't talk about U and D. Okay. They talk about a single parameter that they really care about, namely the volatility. Okay. Sigma. Okay, just a survey. How many of you have heard of, I think you have heard of the term volatility, right? How many of you know exactly what it means? When people say volatility, you know exactly what it means. And by exactly, I mean mathematically what quantity they're talking about. Or have you heard of volatility before? Yes, no, maybe? Did everyone go to sleep already? Yes? Don, you saying something?
I think I've heard of it at some point. Just don't remember.
Okay, no, it's perfectly fine, all right? I mean, I'm not challenging any of you about any of this, all right? Do believe me, I'm pretty relaxed on these things. A lot of these are technical knowledge that I think you should know. I'm just trying to gauge where you are at, okay? So no, not any point. If you say you don't know, that doesn't mean I secretly record that you should get an F in this class or something, all right? If you don't know, let me you don't know, so I can help you out. Okay. So yes, right. I mean, believe me, when I started teaching math finance as a teacher, as a professor, I don't know exactly what volatility means. I mean, I heard of it too, but right, so pretty irresponsible from my side. But that just means that, right, a lot of buzzwords, we don't know the exact definition, but I do believe we should know. Okay. But anyway, right, so let's just accept the buzzword that basically that you accept that, then you reduce, right, the whole dependence into volatility. In other words, the option price is only a function of volatility. Okay, and I mean, even if you don't know what volatility means exactly, you probably would intuitively believe that it's a measure of risk. It's a measure of how risky, right, the asset is. We're talking stock right now. Okay, let's just talk about stock. And so, right, the higher if you were to buy your own stock, you maybe you don't want to buy high volatility stock. I mean, some people would want to buy high volatility stock for different reasons, but we won't get to that, right? But maybe, right, you don't want highly volatile stuff. You want low volatile stuff, low volatility stuff. Maybe, okay, just so intuitively you know what it means. So every stock, right, every company has its own volatility level, okay? So by knowing, right, so the math tells you exactly what this is. That's the math. You know exactly what it is. So then, right, because you know exactly what it is, theoretically you can inverse this, and you got something called sigma implied, which, right, quote unquote, is the inverse function of the call. Okay. I mean, by inverse, by quote unquote, because strictly speaking, the activity of inverting this is not some, easy stuff. But so if you could do this, right, then what you come out, right? So the input will be market price, and the output will be something that you compute. Okay. And so the implied volatility, okay, this, if anything, is a very important thing that people pay attention to. Implied volatility is something people keep watching for when they do trading, when they do any other activities related to, right, a stock. Okay, so implied volatility, if anything, is one of the quantity that comes out of the pricing activity. Okay, is an output, is a good output, an output we look for from the pricing activity. Is this okay? So now let me say right away, right? I'm deeply aware that even this is not the end of the story. This is just like maybe the beginning. In other words, right, implied volatility is posted for you, right? Implied volatility surface is posted for you, right? If you have access to anything like, again, a Bloomberg station, or even, finance gives you something. So in other words, right, your job as a quant maybe is too hard. In other words, like, yeah, even something like this, which I think is not even clear how to do, it all is already automated. Okay, it's already automated. So your job is even more than that. But believe it or not, right, the job of quant, at least, like, a very good quant, a very good job, I mean very serious job, is to calibrate the implied volatility surface. All right, that is a fact. In other words, it's very complicated stuff, but still, at the end of it, right, at the heart of it, it's still you're messing around with the volatile surface. You try to calibrate it correctly, okay, for some product, okay. So the message here, right, that I want to give you, again, so this is probably the finance side I'm discussing, is when you do pricing, okay, when you do pricing, please, right, stay away from this notion that you are divining, you are seeing something that the market doesn't see. All right, that definitely is a very mythical, mysterious point of view that doesn't hold. The orthodox point of view, right, of a quant is that you accept the market price as given, and then you try to deduce information, from the market price, right? And by the way, right, you understand why. I mean, suppose once upon a time there's none of these fancy machineries, then, right, the implied volatility is unobserved. Okay, I think Iran, right, mentioned the word observe. There's stuff you can observe on the market, and there's stuff you don't observe on the market. And at least you should be aware of these things. Okay, so by unobserved, I don't mean that they're not available, right? I mean, you can just look at them from again, Bloomberg or something. But by unobserved, I mean like from the market, right? So from market, whoops, sorry. From the market, from the trading activity. So observed value are stock price, call option price, that kind of stuff. Unobserved values are something like implied parameters. And to some extent, even the Greeks, right? The Greeks, I mean, I guess the Greeks is pretty straightforward to calculate, but it's still unobserved, right? So the job of the quant, right, is to bring out these unobserved values so that, right, the traders or whoever that is can make action on this, because these, right, these are very valuable information. These are internal, right, thing about company that you don't see, but you want to deduce it, okay, from the way they trade, from the way they are valued, so that you can make informed information, okay? So the more precise you can bring this out, the better the trader who you're supporting can make decisions, okay? That's where your value is. Questions? Okay, so now, any questions? Sorry, I should give you some time. All right. By the way, I mean, are these boring discussions? Are these so obvious that I should quickly get to the math, or these are some stuff you want to hear? Because there's a chance that you might know all this in and out already, and I'm just repeating stuff. Is this new stuff? Old stuff? Too obvious? You don't care to know? Just give me some feedback here.
I think it's
Go for it. Yeah.
sorry. Yeah, I think it's good.
Okay. No,
Yeah.
thanks. Appreciate it. So okay, so it's not something old. Okay, Don, you say something?
Yeah, I was about to say the same thing.
You have an echo. I couldn't hear you clearly.
Oh yeah, I was about to say the same thing.
Okay, cool. All right.
It's good to question it.
Right. Yeah, okay. By the way, right, I like to get, I don't know, a little bit more philosophical about these kind of things, because I think it's really, really important that you get the right orientation on what you do, okay? And by the way, when I do believe, in case you didn't know my background, I did, right, try to go to the industry at some point. And I did, go for quant interviews and stuff like that. I did get an offer to work as a quant, but, for reasons beyond my control, I couldn't go to work. So I'm aware a little bit, okay? And of course, I have friends who work as a quant. So of the attitude of people toward, right, what they care for, what they don't necessarily care for, okay? And I think, right, they do care for that you know what you're doing. You know why you do the things you do, okay? They may not care for so much on, the sophisticated math that you carry along. They do appreciate your math, but they also need you to be aware of why you do the things you do. That's why I want to spend some time just explaining this. All right, so let me just also say this, right? So for example, this sounds fantastic and stuff, right? But how do you apply this concretely from something that like Professor Larson has taught you? Can you do this? Have you done this from first semester in math finance? In our program. So can you do this yet? In other words, right, the whole process of finding implied volatility. Okay, so let's see. So first of all, you know how to build a model, right? I mean, you know how to build a binomial model. You have S0, right? So by the way, right, so we're reviewing a little bit about the binomial model. You have S0, right? You have it U and D, right? S0U, S0D, S0U square, S0UD, S0D square, right? And then so on and so forth. So by the way, right, I like to draw a picture. Picture is very helpful for us to visualize what's going on. Okay. So what else do you do, right? Let's take a call option. Okay, let's take a simple call option. So suppose that I want, right? Suppose, right? So this is math, okay, math finance. So what the goal, what you want is you want V0, right? The call option. So call option with strike K, okay? And let's say expiry N, right? N equals 5, 6, 3, whatever you want. So you want V0, right, as a function, abstract function, right, of U, D, what else? S0, K, N, and R, right, like this. Do I miss anything? I hope I don't. Okay. Roughly, I hope you know how to do this, right? What are the recipes? So first you need to probably calculate, right? So, oh, by the way, we need something else too, right? We need something called delta T, right? Step size. Okay. So first you need to calculate the so-called risk neutral probability, right? E to R delta T minus D over U minus D, right? And then possibly you need to do something like this, okay? You do a table, right? Where you do the outcome, you do the probability of the outcome, the risk neutral, right? What is Professor Larson's notation for risk neutral probability? I like to do P tilde to distinguish it from the physical one. Is that okay? When I do P tilde, does Professor Larson do Q or something? What does he do? P star?
He does the same thing.
P tilde?
Tilda. I just have a quick question about the Q.
Yeah,
I don't recognize that formula, the one above.
oh, you mean this one?
Yes, this one.
Oh, okay. Okay, sure. So let's review that, right? So this is Q is a probability of going up. Q is this one right here, and this is 1 minus Q. So
Okay.
Professor Larson used P tilde.
No, for risk neutral, you just use P tilde and Q tilde, but I don't think it went into like P and Q themselves.
You're kidding. You don't know what Q is exactly.
No, I know this, but I
So
didn't
it's
see
fine.
this.
It's fine. No, it's perfectly fine. So let's see why, right? But by the way, this formula I think is something, I don't know, is worth committing to your mind.
Okay.
The reason is this, right? Because it's part of the calibration of the model, by the way. So the reason is this, right? Where does it come from? Okay, so you or someone tell me, what do we mean by risk neutral? What do we mean by risk neutral? What is risk neutral? I want to hear the math of it, and then we'll discuss the finance. And I'll tell you a story of my interview where someone who does not want to hear about my math definition of risk neutral. But what does risk neutral mean? Mathematically. Anyone? Okay, good. Risk neutral means that there's no arbitrage happening there. But how does it help me to find Q? Like, Sherry's question, right? How when you say no arbitrage, okay, I accept it. But how does it help me find Q? Because that, you see, the math is that, right? When we say what is the math, that means it helps us to find something. That you're more talking about the finance, which is good. But what about the math? And then the hardest thing is to connect the math to the finance. Expectation of what equal to 0? Expectation of what equal to 0? Jofan, you want to say something? All right.
Yeah, I mean, I guess the stock price at time 0 is equal to the expectation of the stock price at time maybe t, and times the discount factor.
Excellent. Exactly. That is the definition. Or if I want to be picky, not quite yet, but that is what I want to hear. So in other words, what she did, but it's not really, expectation equal to 0, right? Expectation of current stock price under risk neutral is discounted future stock price. Is that okay? Do we see this? This is not new, I hope. Or in other words, right, the Professor Larson would say something like this: discounted stock price is a risk neutral martingale. MG for martingale, right? Which, for a reason we'll explain, it boils down to something like this. Is that okay? That's not new, right? So that's the mathematics. But, right, how do we unfold this? Well, we unfold this by making it very easy for us. Make k equals to 1. By the way, right, you understand the whole thing here. Sk means the stock price at time k. K delta t, because each step size is delta t. So, k times that. Okay? Clear? So k equals to 1, right, says, well, same thing. S0 equals to E tilde e to minus R delta t S1. Okay? Math. Tell me, what distribution does S1 have? What is S1 as a random variable? Okay, picture. What is S1, right? Here is a picture of S in general, right? What is S1 as a random variable? What distribution does it have?
A binomial distribution.
Okay, how many outcomes?
It depends on the times.
One. S1.
Why? Oh,
right? S1.
Two outcomes.
Very good, right? 2 outcomes. So S1 has 2 outcomes, right? U or D with probability Q and 1 minus Q by definition, right? But that's what we call it, right? So in other words, what we have, oh, sorry, S1 is S0U and S0D, sorry, right? Not just U and D, S0U, S0D, right? So in other words, right, this equation, if you unfold it, will say S0 is E to minus R delta T, S0U times Q plus S0D 1 minus Q. Okay. Cancel stuff and bring this on the other side. E to R delta T is U, let me see here. Q, right, times U minus D plus D. So Q is E to R delta T minus D over U minus D. Okay. Any question? Cherry, does this answer your question?
Yes, I was just confused because I think the formula that we used before was just always like 1 plus R minus D, I think, over U.
Oh, yeah. Okay, so I was using continuous discount. Sorry. Okay,
Okay, yeah.
that's the confusion. Okay, no, okay.
Yeah, I just had never like seen the E term before used in our risk neutral probabilities.
Oh, so I mean the difference then is not some conceptual stuff. It's really about, and I know why. Professor Larson likes to be consistent in terms of discrete time to discrete compounding. So that's why he wants to use 1 plus R, right? For me, but you realize, right? It's just a artificial difference in terms of how we compound our interest. The core of the math doesn't change, right?
Yeah.
Okay, yeah, okay.
Thank you.
Sure. So, right, I mean, if you want to do discrete compounding, then this term will come to 1 plus R delta T. Okay. And then if you are very mathematical, or at least if you are in a math program, you should say that, oh, but of course it's obvious. Why? Because delta T is pretty close to 0, right? It's a small time step. Then by Taylor expansion, okay. So again, fancy stuff, maybe, but right, these are things that like a math person would see right away. That you see discrete compounding when the time is small is approximately continuous time compounding. So in terms of values, if you really calculate it, what I would do and what Professor Larson would do would not be that much different in terms of value. All right. Okay, so now we settled that, right? So where were we, right? We compute Q, right? Risk neutral. And then we want to compute the V0, right? So how would you compute this V0? Well, let's imagine it. So possibly, right, you would need to do a table for Vn and the outcome and the probability, okay? So let's say n equals to 3, just to demonstrate my point. So n equals to 3, right? So the outcome would be something like UUU, UUD, UDU, etc., right? All the way down to DDD. Okay. So how many outcomes are here? Just out of curiosity, not that you need to know exactly, but how many outcomes are here?
27.
That's too many. 8. 8, but let me see here. Yes, there are 8 outcomes, right? 8 outcomes exactly, because 2 to the cube, exactly 8 outcomes. But right, with European option, UUD and UDU, UDD kind of combine to the same thing because the same outcome. So actually sometimes it's 4, okay? You understand, because UUD, UDU comes to the same thing. So 8 is correct, but 8 is a total one if you want to do like, exotic option. Yeah. So yep. So and then you do Vn, right, which is, I don't know, something like this, S0U cubed minus K plus, etc., right? And the P tilde would be Q cubed, Q squared D, and then this is Q squared 1 minus Q, 1 minus Q cubed, right? And then you would multiply this together and add them up, right? You would multiply, and then you would do this count, and then you add, and then you get your V0. Am I okay? I'm glossing over this because I think it's something like this you have seen before. So I'm not really going to the details so much, but you have seen this. So the bottom line is you have already done, right? Or you could do something like this, okay? But don't forget the topic of our conversation. The topic of our conversation is how to find implied volatility, or could you find implied volatility yet? Okay, so notice, right, in this setup, there's no sigma, there's no implied volatility. So where does it come in? We'll discuss this later, all right? But for now, just trust me like this. The typical calibration or the standard calibration for sigma in terms of in the binomial model. Actually, it should be for UD in terms of sigma in the binomial model is this. U is e to sigma square root of delta t. D is e to minus sigma square root of delta t. Okay. So you can look at whole for reference. But for now, right? So in other words, sigma is, so basically, if you care about implied volatility, then you collapse U and D as a quantity that depends on sigma only via this definition, via this relation. So D is 1 over U, right? You know, in that way. So you understand, right? By doing this, I collapse U and D into just one, into only depending on one single parameter. So repeating the above procedure, right? Basically, I have V0 now is a function of stock, right? R, K, those are, you know, superficial stuff. And then sigma. And N, right? N is the expiration. But now I want to find, so now, right? Now the activity is, I want to, so right now the attitudes, these are input and this is output. But now I want to take the exact opposite point of view. In other words, I want to take V0 market as input. And I want to output sigma, right? Of course, right? All the other guys are also input. So all the other guys are also known, right? S0, K, R, and N, right? These are given to you because those are the information of the derivative. You don't know sigma. Of course, sigma is not observed. You want to output sigma, okay? So what I argued before is that you should have learned something like this in Professor Larson's class, even though maybe the computation is a little bit painful. And we'll discuss that, okay? You do recognize that. If you were to try to, right, I mean, I think Chushi said, right, there's 8 outcomes, which I agree. If I try to, 3 is too crude, right? If I try to push that to 10, I push that to 50 outcomes, then that's super painful, right? But anyway, you don't want to do a 2 to 50 table. So anyway, but then let's argue about this procedure first. Did you learn something like this, or do you have the tool to do something like this from, you know, I don't know, you could have learned somewhere else, but let's say from what you learned from our first semester in the program. Can you do this somehow? Suppose you would like to try to do this, what would you do? By the way, right, you should always keep in mind that this is given, right? This is known to you. You already built. You built it, right? Somehow. Using this, can you find this? All right, so maybe let me serve you suspense too. This is where I guess, you know, hopefully you have seen something like this before or this semester. This is where Professor Wu Jun will teach you something, right? This is numerical stuff. Okay, this is numerical stuff. So the idea, right, is that you have already have this thing built in as a computer function, right? You code it somewhere. So this is like a computer function. You know, a program function. All right, and so I hope you appreciate the whole point of programming here, because even I definitely do not want to repeat this calculation once a day for a class, right? If you ask me to do it 10 times, I'd probably rather just quit. So we need a machine to do it for us, right? To do it again, again, again. So you need to have built it somehow as a program, okay? But let's take that for granted. Then what do? Basically, you have a program sitting somewhere where you input these numbers in and it spit out numbers for you, right? Hopefully reliably, according to the scheme you built above. Then, of course, I mean, the naive thing to do is just guess and check. All right. By the way, right, I'm not a numerical expert, so whatever idea I'm talking about here is the simplest idea possible. But simplest idea can be improved, all right? But the most important thing is you start thinking first, and then you figure out how to improve. But if you don't start thinking, then you don't know how to improve. Easiest idea is guess and check. I mean, right, I plug in some random value of sigma, right? All the other ones are given to me now. And then I check, is it close to the V0? If not, I check again. If not, I check again until I get close. All right, now that's as silly as it sounds, but it works, yes? You understand? So the idea is you must have a program you can play with. Then you just plug and check, right? You know, like, so I would say silly, simple, right? Simple, naive idea. Like this is too simple, but it's worth a shot. Plug and check. So let's say you start with some initial guess, right? And you got some initial guess, initial value, right? And then you know, compare with V market, right? And do again. But here, right, exactly now, so you understand my idea, right? How can I improve on this idea a little bit to make it a little bit easier? Because if I just guess blindly, right, the next guess, how do I know what my next guess should be? So let me just maybe for the sake of like discussion, right? Let's say if you do this, let's say V0 that the program output to you is, let's say 0.2, all right, while the V market is 0.18. And that, right, that's not acceptable. That's maybe too far in the scale of the price. What should your next guess be? And how? Does my question make sense? So I suggest a blind guess and check. How do you improve on this? Bisection, excellent. Yes, smaller is also excellent. I love to hear this. Exactly. Very, very nice. Exactly. So let's go with Yunchun first, right? Why do you suggest I should go smaller? That's great. I should go smaller. That's all I know. Exactly. But why should I go smaller? What intuition? Why? On what basis do you say I should go smaller? So I suppose, right, because you see this is smaller than this, which is correct. But is that always true that somehow you see your target as smaller than this and you guess a smaller value? I mean, right? I mean, at least that's human intuition, but you have any better intuition than just, okay, smaller, smaller. So, oh, you know, again, right, in all fairness, we're doing blind check here. So, but do you have any further justification? So maybe, right, 0.15. It turns out it's always true that you should try smaller. The reason is V is an increasing function of sigma. At least for call and put. All right. So here I'm quoting a financial knowledge, but trust me, it's a very standard financial knowledge that the option price is an increasing function of volatility. The higher the volatility, the higher the option price. Did you hear about this before? At least you might have heard about this, right? The higher volatility, the higher option price. So V is an increasing function. Yeah, so that's why, right? That's why, because the target is smaller, it's completely good that I should try smaller one because it's an increasing function, okay? By the way, if you want, right, this is the fancy way to say this is the vega is always positive for call and put. Vega is just the partial of the option price with respect to sigma. So it says the same thing anyway, but you know, some people love to throw in fancy language, okay? But so, and then, right, comes to exactly the method bisection from Alex, okay? Because why? Because suppose that I got sigma 1 to be 0.15, and let's say, right, let's say sigma 1 is 0.15, and let's say V, the output is, let's say 0.1, okay? Again, V market is 0.18. Then what should my sigma 3 be? Sorry, sigma 2 be? What should my next guess be? Exactly, not in the middle, exactly, right? 0.175, and then, you know, I trust that you know what's going on, so I'll just let you check the bisection method. Okay, bisection method. But so again, I'm not claiming anything glorious here, right? I'm claiming the most simplest thing to approach stuff. But my argument, right, by the way, is just that you could do already, right, this baby implied volatility technique based on what you learned, all right? I admit it's easier said than done, because if you set out to implement all these, which by the way may be a good thing for you to do, and which I will, you know, maybe give as a extra credit thing to do, is that you pull together knowledge from different classes, all right? And it's not an easy thing always, right? But each class may teach you only a very particular stuff, right? But pulling it together, right? And usually you have to do it on your own. Is the hardest thing. But you know, when you go to work, that's exactly that, right? They have a job, they don't care where you get it from. You just better find the right tool to do the right job. But I hope, right, by demonstrating, right, the procedure, it's not just a mindless procedure, right? I do the simplest thing, but you know, right, I have a lot of justification, a lot of intuition in between a lot of techniques, all right? So I want to at least orient this class in this way that, you know, I don't care for fancy thing, right? I care that we do the simple thing in a very meaningful way that you understand, right, each step you do. Once you do that, all right, then you know, go learn the fancy method yourself. Professor Wu Jun will probably teach you Newton-Raphson or something even better, okay, for you to do. But you know, as far as I'm concerned, I'm not teaching you numerical. I'm teaching you how an idea of implementation is. So bisection is the painless thing we can do, all right, the easiest thing we can do. Any question? Okay. And by the way, right, it will be a very fun exercise now that I described this, for you to go on now to implement this model and check with the Yahoo Finance implied volatility output to see how far or how close your answer is to that. Okay. Hopefully, actually, right, and I can tell you that the answer should be a little bit close. It should not be too far. But if somehow your implied volatility answer is too far away from them, then you're doing something maybe not quite right, because this is more or less the method people still use. I mean, the model they use is Black-Scholes, by the way. They don't use binomial, but right, still. Any question? So I think we start at 8:40, right? Probably it's a good place to take a break. So let's take a break in for 5 minutes. Is 5 okay? You want 10? 5, 10. Let's do 5, okay? Are you complaining? You want 10 or 5? Anyone? Any difference?
It's all right.
Okay, let's take 5, all right? And then let's get back at 10:05. Okay, 10:05 my time, all right? And then we'll continue.
Okay.
Okay, so hopefully everyone's back. So let's continue. All right. So I described, right, the procedure to find, one procedure, right, to find the implied volatility. But I hope, right, this seems like a typical cycle to you, that basically, right, the cycle is, the typical cycle is, sorry, let me close and restart. What's going on here? All right. Right. So the typical cycle in my mind is like this. And when we apply a quant finance procedure, I believe something like this goes in place. The cycle is first, you have a problem, of course, right? You have a pricing problem. You must understand what a pricing problem is. Then you discuss the model to be used, which then, right, is about the math. You understand the math, what goes on, what is all the mathematics behind this model. And by the way, right, that's the question I asked you about, the risk neutral, the binomial, that kind of thing, right? That's the model. And then you would implement the model. In other words, right, you build that function V that would take in all this input, that output, right, the price. And then you would do calibration, right, model calibration. In other words, then you would fit this model with the data, right, with the market data, and get all the parameters that are, supposed as input before, but now as output, right? So you change the input output. Of course, right, you're only interested in the unobserved parameters, right? And rinse and repeat, right? I mean, maybe after model calibration, I think there's some step about checking or testing, whatever, that you don't think that this model is any good, and then back to a drawing board, right? Do the model, blah, 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 blah. Okay. So the model, right, is where the math happens and the finance happens too there, because you must understand the finance to be able to do the model in the right way. Of course, you see the finance also enters here and there, where your intuition, right, about the finance can help drive the way you build the algorithm, right? And I think you might have heard, stories here and there where, like a supervisor who supposedly doesn't know much about the technical details of the model, just say something earth-shattering, right, to the poor quant who does all these fancy techniques. Well, the point is the manager has a deep financial knowledge, so he knows what's going on, right, how the market is moving. So when he sees something, he knows that something's not right. So, right, the finance cannot be underemphasized here, okay? It is really important. But of course, unfortunately, I'm not the kind of person that can give you a lot of financial, wisdom either, but I'm just saying that, right, the more financial understanding you have, the better you can operate with this model. What else, right? Coding goes a lot in here, right? The moment you start implementing stuff, you better use program. Doing it by hand is just hopeless. Calibration, right, has to do with statistics, finance. I mean, even just statistics and data science. Even the simplest question of how the heck do I download all this data down to my computer to start working? By the way, I don't think it's a simple question to ask, right? Because many times, right, past students have asked me, well, so Bloomberg has this data, how do I get it? And I say, well, if Bloomberg has a way to get it to you conveniently, great, right? Download it to Excel sheet. If not, you're into a lot of pain, because, right, interacting with this interface so that you can download the data down and clean it or whatever is already an art, okay? So that's why I'm not saying each of these steps probably, right, is done by an expert somewhere in the company. But you, right, while in school, should at least be able to have an idea of all these things and be able to pull them together, right, at least in a semi-decent way, so you can have a good grasp on how things go. Okay, so now I want to go back to the implement the model step a little bit, okay? Namely, exactly, right, the part right here where we say we do the model. Oh, sorry, we do the table, Okay. Now, right, do you see that this will quickly get out of hand, even with a computer? In other words, right, I want you to kind of just step back a little bit, right, and imagine how would you code this procedure of pricing, like, with the table into a program? Okay, think about it. Like, right, I have my binomial tree, right? I want to price a binomial tree. By the way, right, you don't have to use a table. This is just a visualization technique. But at the end of the day, right, you are really listing all the outcomes. You sum all the outcome up, right, and average it out. Okay, agree? So whether or not I visualize it or say it out loud, there's something like that in the background. Do you see that this is a coding nightmare? If you don't think about it too much. And why is it coding nightmare? I think, or at least maybe I'm exaggerating. Maybe it's not.
I mean, I feel like the algorithm itself would be simple to understand, but just trying to like make it work in a code would be pretty complicated.
The code, I think, is not that complicated, but you know where the complication happens, or where where does it happen? Where does the complication happen?
I guess maybe when it comes to like determining the outcome and what we're supposed to compute for p hat.
P hat is easy. P hat is always this. P hat is always this, right? So, or Q hat, or Q whatever, is always this.
Never mind.
So the difficulty here, right, is you always want to be mindful of resources, right? I think coding is super important, like, that people care about that, or at least some of the coding question you get on the interview would be how to do something efficiently, right? They care that you know the algo, but sometimes they ask for efficiency. So you realize that, right? Of course, with call and put option, we don't have to deal with this so much. But in general, if you deal with the binomial trees, how many outcomes do you have to model? 2 to the n. Now, that's an exponential growth, right? And it doesn't matter what kind of input you have, it grows very quickly. In other words, storing the tree in a computer would be a nightmare if n is large. Is that okay? Again, right? I'm exaggerating here, right? I'm not a computer science expert, of course. Right, the intelligent way is to deal with it in a way that doesn't require you to store the whole tree in. But right, you see that the naive way of like generating the whole tree out and storing it, the whole thing, would be super inefficient. Is that okay? So right, so there's an art of programming here too, right? Or the math has a lot to say about it as well. You either approach it differently mathematically, you approach it differently computer, in terms of coding. Your pick, right? But of course, my background, I approach it a little bit differently from the mathematical side. Okay, but right, the point I want to say is be mindful of what you're coding, right? What you're coding may or may not be super efficient, which is fine. If you just want to have a toy model just to output something to see, fine. But eventually, is this model scalable or something, right? Is your coding scalable? It is a question you want to pay attention to. So anyway, right, implement the model. So I want just to put one word here, right? Dimension might matter. So dimension here, the word dimension, right, is a vague word. It refers to many things in many contexts. But here what I mean is, right, the number of nodes, right, in a tree, at least what I mean by that is 2 to the n, right? Which grows exponentially, okay? And if you have done anything computer science stuff, you have exponential growth, you should be super worried, right? So what you want to do, right? So it's an alternative approach that may be, right? So, but by the way, this is called the exact approach. In other words, you have a mathematical formula. You are so dead set on solving it exactly. Okay, and I'm not sure if you noticed, but the whole point of learning all this numerical stuff or whatever you learn, a lot of math, is that you sacrifice the precision a little bit. You say, okay, I don't need to get it precisely, I just need to get it approximately. But then you can make your calculation much more easier. Okay. The whole point of bisection, oh, by the way, sorry, no, bisection is too easy, but like some numerical method is because the real equation you want to solve is impossible. But then when you simplify it down to on this grid, right, it looks complicated to you, but calculation-wise, it's much easier. All right, that's the point. So here, right, the whole also the philosophy is we don't do the exact method, but we do some approximation, but it makes the calculation much easier. And the one I propose and the one we will follow, and I hope you will follow, right, is very, very useful, is the Monte Carlo simulation approach. Okay. And by the way, I know something about this, but I'm not an expert either. The right place to learn this course, among other places, maybe is exactly the computational finance course that Professor Larson is teaching right now. Okay. So again, I'm not teaching you the techniques like the super cool technique or whatever. I'm introducing to something that's semi-workable so we can operate in this class. But what's the idea of Monte Carlo simulation? It comes from the idea of random sampling. Okay, and random sampling is super appropriate in our context because if you think about it, we are doing stochastic model. Doing stochastic model means you're doing random sampling. All right, you're generating random variable. So the heart of it, okay, the key idea or the I don't know, maybe I don't want to oversimplify stuff, but maybe, okay, when I say key idea here, hopefully I'm not being over pretentious, but key idea is when you want to compute expectation of a random variable. And pay attention. A lot of pricing that you do, I don't care whatever context you do, it's some kind of expectation. If you pay attention, is some expectation. Okay, unless you do a PD approach, or I noted Professor Larson has some OD approach. Maybe he mentioned that's a different one, right? That we will get to later. But of course, if you do the PDE or OD approach, then Professor Wu Jun, right, has a lot to talk to you about on how to do it numerically on the PD side. Okay. But if you do the stochastic approach, meaning you do the expectation approach, then right, simulation, random sampling is right there. And what the key idea is just simple like this. When you want to do an expectation, you just basically sample, right, the random variable n times independently over and over again, and then take the average value. Then that's approximately close to the expectation. Okay, and of course the name of this is called the mathematical name is the law of large number. Okay, so let me demonstrate an idea for you. And we will explain, but at some point, right, and actually we will get to this very soon, if not today, the next week, is this Black-Scholes model. Okay, Black-Scholes model. The Black-Scholes model says, and I won't explain to you why, but the stock price is S0 e to the r minus 1/2 sigma square t plus sigma w tilde t. Okay, that's the stock price model. Okay, so that's the mathematical model. Now, if I want to do a call option price, then V0 will be expectation under risk neutral, which, by the way I write this right here is already in risk neutral format. Okay, will be expectation of e to minus RT ST minus K plus. Assuming, of course, the expiration is at time t, like little t, right? I should write big T, but okay, let me write big T. Oh, sorry, R time big T. Okay. So This actually, if you need to work it out, is a pretty tedious exercise that I don't mean anything here, but I'm pretty sure like all of you guys will probably spend at least an hour to figure out, okay? Because frankly speaking, if you don't know what you're doing, then it's a pretty convoluted problem. But of course, this has a formula, the famous Black-Scholes formula, right? It has some, S0 ND plus minus K e to minus RT and ND minus whatever. I'm not discussing this formula because, of course, this is the exact formula. But suppose once upon a time, you don't know this formula. You don't have this, okay? All you have is this expression. What can you do? What can you do is surprisingly a lot, because if you look back on the randomness of this, where does the randomness come from? So I haven't discussed to you, right, what this object is. This is exactly what is called a Brownian motion. The W tilde T is a Brownian motion, right? All these are familiar parameters. R is the interest rate, sigma is a volatility, T is a time. So these are constants, right? So the only place that randomness enters is here. So all you have to do in the expectation here is somehow to capture this randomness or sample from this randomness. Again, right, for a reason that we don't discuss or from the definition of Brownian motion, W tilde T has a normal 0T distribution, okay, which can be written as square root of T times normal 0, 1, standard normal, okay? So the scheme, right, and the simplest scheme, the Monte Carlo scheme, the simplest thing you can do is to first, right, let's say sample 1,000 IID standard normal. Okay. How? How is Python, MATLAB, any R, any standard program this day, right? We just put in a command, it's output 1,000 numbers for you, right? Of course, the art of generating these numbers is also something worth discussing, but we'll take it as given, right? You can go to a program, say, I want 1,000 standard normal, I'll give it to you, okay? And then you plug them in to the, so basically you generate 1,000 value of this guy. So I should call it S big T, right? Using this formula. Okay, so let me rewrite for you. ST will be S0 e to R minus 1/2 sigma square T plus, but now I need to be careful, right? Square of T times Z, right? Sorry, Z, not ZT, right? Z. Z is the standard normal here. So, right, for 1,000 values here, I get 1,000 values here. Of course, right, accepting all these are input. Okay, then what do I do? Expectation, right? Expectation. So I'm almost there actually. Now it's just decoration. You basically you generate. So conceptually you do this, but coding wise you can combine the step maybe. You generate 1,000 values of VT by doing what? VT is max, right? This is computer language, but of course it's just ST minus K plus. And then you output V0 to be 1 over 1,000, right? E to minus RT, the sum of the 1,000 values of VT. Does this make sense? Any question here? So, right, the beauty of this is, notice all these are automated, right? I mean, you just have to really chase the formula of the expectation. And if you do this high enough, then the answer here is pretty close to this answer, guarantee. And then we can do it. We can check that, okay? And maybe I can ask you to do some check like that on the activity, on this Friday. But again, right, the beauty is, right, to do this, you need a lot of math, a lot of, manipulation. It's not much. Of course, right, that's oversimplifying stuff because, to earn your money, maybe you need to make this more efficient or something, right? Generate less random variables, make it converge faster. We won't discuss that. But, right, it bypasses all this calculation. Okay. So now, back to our binomial model, right? Is there some similar story, right? Because again, remember, the question is, right, I have this table. I do not want to do a table because a table is to facilitate calculation of V0, right? Like this. So how do I do this? Using Monte Carlo simulation. So using Monte Carlo simulation, right, I have, so but in terms of the binomial model, right, what I have is, what I have is, right, that, so V0, right, is risk neutral. It's still always the same formula anyway, right? E to minus R, right, N delta T, right, and then Sn minus K plus, right? So actually, one of the, I keep saying beauty, right? Too many beautiful stuff here. The beautiful thing about math, at least the pricing formula, is you notice it doesn't change, right? The pricing formula is always the same. So if you understand pricing from the mathematical approach, okay, not the applied stuff, is that it's always the same concept. It's always the same concept. Of course, what changed? What changed is the model behind the underlying, right? That's why you learn different models. It's the same formula, it's just different models. So here, right, in this, the model is the Black-Scholes model, or some people would prefer to call the log normal model, right? Here, the model is binomial. In other words, right, roughly speaking, Sn has a binomial distribution, okay? Not exactly, right? If you think carefully with it, it's not Sn has the binomial distribution, but so here, right, the model is the number of ups, right, has a binomial distribution with n step and success q. Is it okay? Do you follow?
Yes, I'm following.
Okay, cool. Thank you, Sherry. So, right, so the scheme is same as before. Basically, right, you generate, let's say, I don't know, 1,000, right, binomial NQ. Then you generate SN, 1,000 SN. But be careful here, right? You got to pay attention to how this is related to this. So this is the random source, right? You can call it the noise if you want, not exactly, but right, this is a random source that drive your model. So how does the random source enter, right? The random source enters like this in the Black-Scholes model. The random source enters like what in the binomial model? Well, it will be S0, right? So U, right, to a number of ups, and then D to the n minus number of ups, because that's the number of down. Of course, UD is a given input right now. Is that okay? And then, right, then you generate 1,000 VN, and then you average and discount to get to V0. Okay, question. So let me show you an implementation of that on Python, all right? Python is my go-to program, not because I'm good or anything, but because I think it's pretty standard these days in industry to use Python. And what else do I want to say here? That you sorry, I know what I want to say. So you can use MATLAB or whatever programming of choice that you want. Okay, in this class, the program I use is Python for demonstration. And if you have MATLAB question, I may or may not be able to answer you, right? Python, that doesn't mean I can answer you either, but I'll be more willing to kind of look through the code with you or something, right? Again, right, I think I will ask you to do these kind of things, coding some way as extra credit project, okay? Because again, I think it's super important for you to be able to implement some of these or have some experience. So this will be part of the class, right? As an activity, that's very important for you if you want to get a good grade. All right, so let me see here. So let me share my new screen. Okay. I realize that the code is a bit small. Can you see all right? Looks okay? I cannot see my chat anymore. Shout out. Is the vision all right? Do I need to enlarge or something? Good?
It's a little bit small, but we can still read it.
Let me see. Can I enlarge this? Oh, cool. Better, Cherry?
Yeah, that's a lot better. Thank you.
Okay, awesome. All right. So NumPy so Python, right? Again, one of the beauty of Python is it has a lot of package that a lot of things has already been pre-coded for you. All you have to do is just to find the right tool. A lot of times. So NumPy is a package that I think is supposedly work as MATLAB. So that's good news for you. Those of you who have done more work in MATLAB, that the structure of Python in terms of coding is similar to MATLAB if you go through a NumPy package. All right. So here, right, this is the, so I said 1,000 in my notes. This is 100. You can do 1,000 if you want, right? This is a step size. Sorry, this is the number of steps. So n equals to 3. Remember, I tried to generate that, right? So this is step size. And here, right, because I want to approach it from the volatility point of view, so I define U and D, right, as e to the sigma square root of t, right, square root of delta t. You see, up and down, right? Initial stock price, interest rate, and here, right, is the so this is the strike, right? And this is the risk neutral probability. Okay, and so these are just the input, right? Now, of course, here I'm just writing something like this. Eventually, you want to turn it into a function, right? So that you can just call it and then, do the bisection method, for example, right? But for now, I'm just interested in doing the Monte Carlo demonstration. But so here, right, these are the inputs. And so here, right, is where I do the random sampling, right? I do the random sampling where, right, that this is a number of ups. This is this is the sample size. But by sample size, I mean, right, basically a sample, there are two samples going on here, right? This is the number of steps rather, right? And this is the how many binomial you want to generate success probability. Okay. So of course, right, I don't have to teach you this. One of the good thing to do in terms of programming is just see what the heck you're getting. Of course, right here, I need to dial back to like 10 or something to see if like the number makes sense and see what you're getting, right? So run right here, right? So this is the number of ups. And of course, right, there are 10, do I get 10? Yeah, right, 10 outputs because I have 10 sample of 10. And then, right, the numbers are between 0 and 1, seems pretty good. So yeah, right, so that's that. I don't know what Q is, so let me see what Q is. 50%, so that's why it's like that, right? So anyway, if I skew the volatility higher, what happens to Q? Oh, it doesn't change that much because my delta T is too small. Step size too small. Let me change this. Huh, okay, it's funny. Volatility is really high already, but it doesn't change. Let me see. Wow, I'm a little bit wondering why Q is hovering between this and this. Anyway, it doesn't matter, right? That this is so this, right, is how what I mean by generating a random sample, right, of the binomial. Okay, and notice, right, it's random because every time I run it, I get a different output, right? Okay, and then, right, so then this is why I generate the S, right? Generate the terminal stock price, right? So this is the notation of power, right, in Python, power, right? And so let's see the S, right? Probably nothing super enlightening to see, but right, these are exactly the what I call it, the end outcomes, right? That I would get from this n time sampling of this thing, and then, right, this is generating the V, right? Generating the V, discounting, right, and then sum, right, all the stock price divided by n. Okay, so when you do this, right, you should do a reality check. A reality check would be because you could make mistake in your code. Let's say when k equal to 0. Okay, if k equal to 0, and I will print out V, right? Okay, let me do k equals 100 for you first. Okay, and let's say here is 1,000 trial. All right. Oh, I'm printing out something else, Q. Let me not print out Q. Okay, like this. So this is the V, all right? Does this seem to make sense? Hard to say, right? So, but then we should do some reality check. We should do some reality check. So can you propose some reality check? By reality check, I mean changing some of these parameters and see if the output matches with my intuition. And by the way, right, notice this is not an exact answer because I'm not exactly calculating the binomial model out. I'm doing approximation to the expectation, okay? But it's pretty good, I think, all right? But then what kind of modification I can change on these parameters to check on, whether or not the output makes sense. By the way, for some reason, I cannot see the chat, so please shout out into the microphone. I guess when I go back to the lecture, I can see the chat, but if you type something in, I won't see it. Any modification you want to suggest to check if our code has no mistake, or at least seems okay. Johan, you want to say something? I can't hear you.
Maybe increase the sigma.
Great, right? Because if you increase the sigma, what do we expect?
Greater the V.
Yeah, so let's try that, right? Let's try 0.5. So 0.009, right? 0.065. Let's try again. 0.11. So at least, right, reasonable. Okay, good. Any other check? So right, exactly, this demonstrates that increasing function of sigma that I talked about. Okay. Notice, right, there's nothing that I coded in here that implicitly says increasing. So my code must be at least decent. All right. Anything else? Anyone wants to suggest? Maybe changing the strike, right? Now, how the option move with the strike is a little bit, right, not that straightforward, but there is a very, very particular one when k equal to 0. When k equal to 0, what should the answer be? Yeah, Jufan?
Initial stock price.
Correct, right? So it should be S0. Ooh, it doesn't come as I advertise. Hold on. Oh, that's super wrong then. That's super wrong. Ooh, see, you could. Now I do a reality check on myself and I did it wrong. Hold on. K equal to 0, yeah. Why does it come like this? Maybe this command doesn't work that way. So let me do this, all right? Let me do just S. Yeah. So if I just do S, right, then you see, so here, right, is the same effect. I sum up only the stock price, right? That's the same as K equal to 0, right? If I sum up only the stock price, I get 99.78, which is close to 0, which is close to 100, right? And that's what I mean by it's an approximation, meaning that, right, this is a random sample. So the more you do the sample, right, the more it's closer to the supposed answer, but it may not be. So what the error is maybe when I do this, I think the function does not operate the way I want it to be or something. Okay, so it's a good thing on myself too, right? That I did something wrong here. So let me just check one thing, all right, and then we will. So the max, this is not the max then. Something is weird, right? Oh, let's do this. It does not output a vector. It just output a number. That's weird. So I think I need to go in. I was being lazy here. I was just doing this. So I think, right, it should be a vector. So here there was some mistake here. All right, so it should be a vector like this, right? This is a stock. So like this, for example, like this, right? Like this, it should be like this. But when somehow I apply the max function, it only reduces it down to a number. So I think that's wrong. So I need to go back and see how I can do this. Okay, so apologize for that. But the point, right, I hope is, besides from my, kind of embarrassing mistake, you understand the point, right, of the Monte Carlo simulation. So that, right, you generate the random sample, you generate the whatever you need to do for the stock, you generate the value, and then you sum them up and output the answer. Okay, and this is the basic Monte Carlo simulation thing technique that is very helpful for us to at least implement our model in a simple way. Okay, so I will fix this and I will post that later on. Apologize. All right, so let's go back to sharing our screen. All right, so let's see here. Okay, I can see your chat now. Cool. All right, so any question on that? Any question on that? So I mean, I not an excuse for myself, but right, that demonstrates that we should be more familiar with the coding environment to know what the function is doing. So I was thinking the max is doing its job, so I didn't bother checking it, but it turns out, right, that the max wasn't doing what it's supposed to do. So, all right. Okay, so what else do I want to tell you now? So class is supposed to end at 11:40, right? So we have 1 hour to go. Let's talk about something like this, okay? Another component of the binomial model I want to talk about before we move on to the continuous time model. Let's talk about meaning of U and D, and also the structure of the binomial model. Okay. So first of all, right, can anyone tell me what does U and D mean? Now, I know what it means roughly, but do you have a name for it? Do you have a financial name for it? Like something that just bring it home. What does U and D supposed to do? Supposed to tell you? So I know it just how much the stock goes up, how much the stock goes down, right? But do you have a better name for it? You have something that just say something? So the keyword I'm looking for, right? And by the way, I'm not like springing word on you, but this is really what carries it home, is a concept of returns. And there are two types: percentage return and log return. Okay, have you heard of this concept before? Now, if you're in a finance class, I think you will learn it like in freshman or something. Like that's the first thing, right? And also, by the way, right, when people invest in things, right, they're not concerned with the value, right? They're concerned with the returns, right? Because, for example, if you buy Amazon stock and it earns you $1 a day, that's not the same as when you buy some, I don't know, really cheap stock and it earns you $1 a day, right? Because Amazon being so expensive right now, earning $1 a day is not much return at all. But if you say spend $1 on a stock and earn $1 a day, that's 100% return. Okay, so return, right, is what people look for, not the level of the price itself. Okay, so how do we define return mathematically? Return can be defined for anything, okay? But here, let me just, for simplicity, talk about stock. So suppose you have S0 and ST, right? So this is current stock price. This is stock price after the period. And let's say the period has length delta t, okay, or t, doesn't matter, delta t. Then the return, right, percentage return over this period, okay? Because return are different over different periods. I hope you see that, obviously. Is, let me call R, right, R1 is, and return should be on from the whole period, right? Would be ST minus S0 over T, right? Simple. You look at the difference in price divided by the time, right? Log return, so R2 will be the natural log of ST over S0, 1 over T. Okay, so the log return, right, is going to be basically 1 over T. If you want, I mean, this is the good one already, but log ST minus log of S0. Okay, now, are these one and the same thing? Are these one and the same thing? Is log return the same as percentage return? mathematically, no, right? Of course, one is a ratio, one is a log function. But you understand that if t is pretty small, then they are pretty close to each other, right? If t is pretty small, the length of time is pretty small, they're pretty close to each other. But on the other hand, is that the end of the story? Like when t is pretty small, then they are pretty close to each other. That's not the end of the story even, because it turns out that I think one of the returns is kind of always higher than the other. I forgot which one, but we'll explain that, okay? There is a connection between these two returns in a funny way. In other words, if you look at percentage return, I forgot one of them, is always higher than the other a little bit. So if you want to impress your investors, right, you can always choose to report. I mean, of course, people know this, so you probably don't want to do this, but you can always report one type of return over the other. It makes it look a little slightly better. Anyway, right, applying to the model, what are we looking at? So applying to model, right, you have something like this, that basically, right, let's look at, say, S1, right? S1 is like S0U or S0D, right? That's the two possibility. Or I would like to do this. I think Professor Larson used the notation epsilon, C or something, but I would like to use this. S1 is S0 times X1, where X1 is a binomial, right, with U and D, with some probability Q and 1 minus Q. Is it okay? So this is a random variable. Okay. The reason why is, like when you do S2 is just going to be S1 times X2. In other words, right, each time I just have to multiply a single binomial or Bernoulli random variable into the previous one. So the structure will be a string of random variable string up like this, where these two guys are supposed to be independent but identical. Is this okay? Any question on my notation? Any new thing here? Okay, so I'll take that as a no. So investigate, right? Try to match up the concept. Try to match up the concept. What do you see, right? So let's take S1, right? So if I take S1 minus S0 over T, right? Over delta T now, because delta T is the length of the period. So basically, right? So there are two outcomes. I can just capture it by talking about random variable. So if I do that, basically I got S0, right? Oh, you know what? I apologize. Bad mistake. 1 over T divided by S0. I'm sorry. Okay. Otherwise, it still has a scale. So basically, you look at the difference in stock price, right? It's gain or loss with the original price, right? So for example, if original price is 1, if you gain $1 per day, that's why it's 100% return, right? But if you have $1,000 to begin with and you gain only $1, like roughly speaking, right, that's only 1 over 1,000 return, right? So yeah, there's a division by S0 here, okay? I made a mistake. So, right, it's going to be S0, right, times X1, so here, 1 over delta T, right? So S0 times X1, right, minus 1 divided by S0 and 1 over delta T. Okay. So that would be, roughly speaking, right, X1 minus 1 times 1 over delta T. So the U and D, right, besides this kind of scaling and centralizing, right, is exactly related to your return, right? U is typically bigger than 1, right? So U represents your positive return. D represents your negative return, right, over a period. Is it okay? Same thing, right? If you take the log of S1 over S0, right, 1 over delta T, what you do is 1 over delta T, right, log of S0 x1 over S0. So basically you take the log. Okay. And so you see then the difference is, right, but you see it's the same thing. U is bigger than 1. U is bigger than 1. So if you take the natural log, it's a positive number. D is a less than 1, again, typically, right? Then you take the log is a negative number. So again, the analogy is the same. And also, of course, right, if you're good with your calculus, you see that the natural log function and the function a number minus 1 is close if that number is close to 1, okay? Meaning U and D are small, or like delta T is small, that kind of thing. So the U and D model is exactly the returns, okay? Exactly the returns, okay? I mean, exact is too much, but like it's deeply correlated to the returns, okay? Now, let me mention one aspect of thing that it may slip under your radar. That when you model the SN, right, the stock price at time N, so you would do this, right? S0, X1, X2, etc. up to Xn, where these are the Xi are IID, meaning independent, identically distributed. Is this okay? I mean, first of all, is this notation clear? You follow what I'm talking about? I'm not describing something new. I'm just turning to a stochastic description of the model. This is okay? Not new? You understand what I'm talking about?
Yeah, I understand.
Okay. So then the question is, why? I mean, I know it's like a silly question, but why do you do this? Why IID? Why independent, identically distributed? Or, you know, of course, right? When you ask a why, it's really a loaded question. Why in what sense? Why mathematically? Why what? Mathematically, it's quite clear. You know, independent, identically distributed random variables are the easiest thing to deal with. But don't forget that you are not in this business to do the easiest thing possible, because people will never pay you the big buck to do so, right? You're in this business to do the right thing or to do the difficult thing even. So when you do something like this, right, you better have a reason for it. And the reason maybe is empirical reason, all right, or something from reality to back you up. So just out of curiosity, right, does anyone have any idea on what empirical basis you can justify this model? And by the way, right, this is what I mean when I say I teach you a model. I want to connect it with, you know, the meaning and reality. A model doesn't live until you try to see what it does out there. All right. If you just do the math, okay, great. But you're probably right. Again, just in this business, you need to kind of see what's going on out there to connect with the model. Any observation that you know or something that would back this up? All right. So is this right? That the xi are deeply related to returns, right? The xi are deeply related to returns. Now, you definitely should have been familiar or have heard of this idea of financial data series, right? Financial time series data. It's a fancy word to say that you collect a history of stock price over a period of time. Okay, like you collect the daily stock price of Google over the last 30 days. That's a financial time series data. Okay. But that's not the end of the story, right? You collect this daily stock price, right? You know, like say Google daily stock price. That's not the end of the story, right? What do you do with this, right? You have 30 data points, okay? 30 data points, like let's say, you know, you have S0, S1, right, up to S30. Tell me, right? So first of all, let me say this, right? The one very Typical name for this is the historical price, right? Historical price. Historical last 30-day price or something. What do you do with this? Look at it, admire it. What do? What's the first thing, or what's the something you can do to start studying this object? I mean, bring in your binomial model, to bear in mind too, right? What do you do with this? Or Black-Scholes model, if you will. If you have seen that, you want to discuss that. What do you do with this? Suppose, right, your boss say, okay, here's the historical price of company, ABC. Tell me what's your opinion? You think it's okay, good, bad? I mean, of course, right? I think some of you will say something like, and wait, right? Again, right? This is fine. You probably draw a chart or something, right? This is a path of last 30 days. But is that enough? Is that scientific, or what can you say here? Right? You see a path. I mean, of course, right? If the path keeps going up, I think even I would say, wow, that looks pretty cool, right? That's pretty good stock. But I mean, I don't think, right? Most stock probably will look something like that over the last 30 days. Then what do you do? What can you do? All right, so not sure if it's a loaded question, but one thing you should immediately do is just look at daily returns. Right? In exactly the same spirit as I talked about above. In other words, right, return on day one, let me do R0, right? Something like this. There's some unit of time, right? Let me just skip that, something like this. Technically, usually, I think the standard measure is an annual return, if I'm not mistaken. Right? You can talk monthly return if you want, but so depends on how you want to do this, right? The delta T is calibrated to that return. I think the typical one is annual return. I'm not sure monthly return is used so much, but so this will be 1 over how many business days there are, 200 something, 252. Am I wrong? Business days in the year. Okay, but anyway, right? For our purpose, it's just some number that you scale. Right, so etc. Right. Okay. So you get 30 stock price, you get 29 returns. What do you do with this? What do you do with this? So these are, by the way, right? They're daily percentage returns, right? Your fund, you want to say something?
Oh, maybe we can find the mean and the variance.
Very good, right? You can look at R bar, and you can look at, sigma square of R or something, right? Hat, whatever, And right, I think here you already see some. So this is the mean return. And by the way, right, it's well known that mean return is pretty close to zero for many places. I mean, if the scale is small, daily return is close to zero, even for well-known stock, okay? It's only on the big scale, like annual return, and you pick up to 5% or something. Daily return is like close to zero. So R bar is about zero, nothing to say home about that. But this guy, right, guess what it is?
Volatility?
Volatility square. I think volatility is standard deviation, right? So exactly, yeah. This is the square, right, of volatility, okay? So, or of course, the estimate, okay? So this, by the way, right, so let me take out the square, okay? So this is called the historical volatility. Okay, so remember, right, I asked if you know precisely what volatility is. So here's the place to answer it. Volatility, roughly speaking, is standard deviation of return. I mean, that's as precise as it can get, but of course you can ask what type of return. I don't know. I'm not sure if there's a consensus on that, log return, percentage return, etc. Okay, but it's a standard deviation return. Okay, so that's where it is. And I hope at least you see why you care, because it's return that tells you how the stock does, is business, right? Not the price, the return. And then, right, the volatility of the return is at least one measure of how risky the stock is. Okay, so right, this is a measure. Okay. Now, of course, notice, right, I'm very careful to separate this from the implied volatility. Okay, this is historical. And a very good question for you to contemplate, and I'll share with you the answer at some point, is what's the difference? And I hope you appreciate that there's a difference here. The approach of historical volatility estimate and the approach of implied volatility estimate are two very different approaches. Okay, of course they have very different meanings too. And do they equally have values? Do we care for one? Do we don't care for the other, etc.? Right? Why? And of course, right, all these questions are financial questions, and not really necessarily mathematical questions. But why? Okay, and you should really care about these kind of questions. Anyway, right, back to that question later. But what I want to say here is this, right? So, and by the way, right, notice what are you doing here? You're doing statistical study, okay? And you see immediately why, right? Statistics is you know, behind the scene too. You can't ignore that kind of question. But so Joe, right, suggested a simple thing to do. Any more sophisticated technique, right? Not that we need to get there, but right, beyond mean and variance, what else can you do with this data? Remember, right, in connection with this question. So in connection with this question, there is an implication that the returns are independent. Okay, that's what the model says. It says that returns are IID. So the model that we are saying here, right, but even though we write the X, we're saying that daily returns are IID.
I have a question.
Yeah.
So in the daily returns part, so should each returns be the S1 minus S0?
Yeah. I apologize. Thank you, Joe. Thank you. I mixed a lot with the thing. Yeah. Thank you. This is the percentage version. Thank you. Yeah. Yeah. Okay. So returns are IID, right? Returns are IID. But what do I want to say here? Is that real? Is that true? Right? Your job, I mean, maybe part of your job, if you're into data science and kind of, you know, cool stuff, is there is a statistical hypothesis. You use the data to back up, to validate that statistical hypothesis or not. And by the way, right, the term statistical hypothesis is a technical term or a fancy term, but it just may be driven by your model, right? You write down your model like that. That's what you're assuming. Okay, and everyone has a right to challenge your question, like, is that real? Is that true? Okay. Now again, right? I'm not pushing you, putting you on the spot, meaning like, oh, how come you don't know this knowledge? No, right? These are really complicated, not complicated stuff. It takes a while to accumulate. Okay, but I just want to at least direct you to the direction that you definitely want to accumulate this knowledge. Okay, before you get out of school, hopefully to kind of build up, you know, that first potential for job. But so how would one go about testing this, right? Using this data, can you do, or at least do you know some names that at least this way you come and look it up? This kind of question. So, right, you could do some independence tests, or you can do some correlation test, all right, among the time series. It's referred to as an autocorrelation, maybe, right? So you can do some correlation test. And again, right, these are parts and parcel of some package, like R package, time series package that you can do. And exactly, right, that brings up the name of something called time series. Time series is a series study. I think, do you do that a little bit in econometrics, 1 or 2? I have no idea what you're doing right now in econometrics. Do you do time series or regression or something like that? Anyone take, I think you're supposed to take econometrics, right? No idea. All right, but so time series, right, is exactly where, right, you look at the data and you try to fit a time series model on it and test the assumption of time series, right? And time series, right, so when you say IID, in terms of time series lingual, you're saying that the returns are like white noise, okay? The returns are white noise in some way. So of course, right, that sounds a little bit disturbing, right? How come return are just white noise? You think that, right? Exactly what drives people crazy is they think that return has a pattern, right? You know, that from this I can predict that, etc. Right? If you analyze deeply, what people tend to say when they say they can predict stock price is they can see some pattern in the returns. And so if you cast that, right, into time series language, that's basically, at least there's some model there, right, for you to fit the time series into the returns. ARMA model is one thing I can think of. A REMA model is another. AR, right? AR and MA, moving average. AR is aggregate. I forgot what AR means. And then you can have like stochastic volatility model like Arch and Garch. Okay. Again, I'm not trying to impress you with names and stuff, but basically that's a whole bunch of area where, right, the series study is how to model the returns. And of course, if you don't model the return in terms of a white noise, then the binomial model, right, goes to a different way. Okay, you have to recalibrate your binomial model. But okay, that's not right. That's not what I'm here to teach you, right? We'll just assume the binomial model because there's enough work to do it. And roughly people still use the binomial model, all right? So roughly, I think, right, on a usual period, nothing unusual, like not like, you know, recession or something, then returns are roughly IID. You can do that, right? But there's some justification here, all right? And at least I just hope that the point of the discussion here is that you can observe the data, or at least you should be aware of a connection from your model to the data, and you're willing or you're able to look up some further part to back up, right, the model assumption. That's it, right? If you don't know it, you go learn it. Not that you have to know it right now, but at least you should know the connection. Okay. So so returns, okay, returns is the key to model a underlying the stock, at least for this class. So if one thing, right, the mathematical message, the modeling message that I want to say, right, aside from the time series justification, is that modeling assumption that we make in this class or in our model is that returns are IID. Even you will see this even in the Black-Scholes model. At the heart of it, that's what it says. Okay. Oh, sorry, I need to be careful here. So returns over, right, identical non-overlapping period. Okay, because of course, say if you have, you know, 2 days here and 2 days there where they have 1 day in common, then of course they're not independent, right? But if you have, you know, these 2 days and that 2 days that they are not something overlapping, then they're independent. Does that make sense? But right, so these are kind of like common sense stuff. But so anyway, right, that's enough. Now I will switch gear, right, to properly what belongs to this class, which is continuous time model, right? Brownian motion. Any question before we continue with this, before we switch to this? All right. So first, right, you should have an idea of how continuous time model arises. Okay, where does it come from? So, right, the whole idea of model a binomial model is like this. You have a fixed horizon, big T. Okay, you have a fixed horizon, big T. You have the current time right now. So big T is like 3 months. Okay. So you decide on how many time steps you choose to model this time horizon. Let's say if you're lazy, you say n equals to 3. Then clearly, right, your delta T is 1 month. Or if you use the annual unit, then it's 1/12, right, year, or something like that. Okay. So then, right, then you go and calibrate, right, your U and your D, that kind of thing, right? U is e to sigma square of delta T. D is e to minus sigma square of delta T, right? And then you, right, build your x1, x2, x3, and then you generate your S1, S2, S3, etc., right? But notice, right, that, like I said, n equals to 3 is too crude. You decide to, well, let me do n equals to 10, okay? And then delta T is, I don't know, 3/10th month. And then, you know, right, and then n equals to 100, you see the story, right? Of course, I did mention, right, as the number of nodes get large in terms of programming, in terms of calculation, it gets unwieldy. So, of course, right, the one way to do it is with the binomial, you know, sampling that I just show you. But even, right, for computer, if you sample a binomial 100, the computer might get mad at you because 100, you know, sample may be a little bit large. Maybe not, it can handle it, but a little bit larger than that, like a 10,000, right? If you sample from a 10,000 binomial, I think computer might get mad because part of it is going to be, you know, 10,000 choose something, which is a very large number. Anyway, right? But here's another mathematical angle, because the moment, so of course, right, when I do this, one aspect of things is delta T keeps going to 0, right? So at some point, right, it gets to daily, and then it gets to like even second, right? I mean, if I keep pushing, right, the number of periods, then, right, so of course, pay attention that very important that I fix this, right? I fix the time horizon. I'm not pushing the time horizon to infinity. I'm fixing the time horizon, right? I keep chopping down the number of periods. So eventually it becomes like a split second data, right? But if you push it like that, right, then mathematically, right, there's always the idea of asymptotic, meaning that your model, right, starts to become continuous. It starts to become something else, okay? What is that something else? So waving hand here, because I'm not interested in showing you the math, but basically, right, in all these steps, notice one thing is you have the returns, right? You have the daily returns here, you have the returns here, you have maybe the monthly returns, daily returns, etc., right? And then even secondly returns. These returns are always IID, right? These returns are always IID, okay? So when you push them, right? When you push the delta T go to 0, when you push delta T go to 0, right? Oh, and maybe let me say this too. When you push delta T go to 0, then the return, right, it's going to be very small. Delta T goes to 0, then the returns become very small. But one more thing that I want to observe is this, that log return, right? Log return has this property. Okay, like this. That suppose I want to total, let's say 0, 1, and 2, right? What is the return on from 0 to 2? The return on 0 to 2, right, will be 1/2 delta T, right? And then log of S2 over S1, which is 1/2 delta T log of S2 minus log, sorry, S0, right? Is that okay? This is return from 0 to 2. On the other hand, right, if I look at return from 0 to 1, that's 1 over delta t, right, log of S1 minus log of S0. And then if I look at return from 1 to 2, that's 1 over delta t log of, what is it, S2 minus log of S1. Is that okay? So what happens when I sum these guys? If I sum these guys up, then you see that this and this cancel, and I got log S2 minus log S0, aside from the fact that this is this. So in other words, right, I get something like return from 0 to is return from 0, 1 plus return from 1 to 2 divided by 2, right? So the log returns, right? The percentage return doesn't work as nicely, but the log returns, right? If you add them up and average out, then it becomes the returns over the big period. Okay. Now this coupled with the fact that the returns getting smaller and smaller. Okay, and this is where I'm waving my hand, but I'm quoting this. Okay, there is something in the mathematical literature called the central limit theorem. Okay, that says that if you have a sequence of IID random variable, okay, now the context is that n is going to infinity. Okay, you push n to infinity, then the sum, right, of xi minus mu divided by let me see here, sigma over square root n, right, is going to converge to normal 0, 1 as n goes to infinity. Okay, so never mind the detail. We don't need to use it right now. But the point is this, that when you sum up IID random variables, as long as the mean and variance are fixed in a certain ways, or if the scaling is done right, the limiting distribution is going to be a normal distribution. Okay. Notice that when we push the, when we push the binomial model and we divide the time interval into smaller and smaller period, it has exactly that phenomenon going on for it. In other words, when you push the delta t goes to 0, right, the big returns, or the return over any long period, is going to be the bunch of sum of smaller returns and average in some way. So with waving hand, I'm saying that the returns in the limiting case, okay, as delta t goes to 0, returns will take normal distribution. Okay, returns are still IID. In other words, return over non-overlapping periods are still independent, but before, right, returns has a binomial distribution. But now when you push delta t goes to 0, the return will have a normal distribution. Okay, that's all I want to convey. And if you want to really justify it, you will dig up central limit theorem behind the scene to justify what's going on. Any question here? Okay, so this explains the incoming of the Brownian motion. So before, right, before in the binomial model, then the driving force is the binomial random variable. Okay, the driving force is the binomial random variable. Here, the driving force is the Brownian motion, or the normal random variable. So I want to introduce, right, the rigorous concept of the Brownian motion. Okay, so Wt is a Brownian motion, Bm, okay, if the following happens. At time 0, it takes value 0. if you look at the difference of the Brownian motion, it has a normal with mean 0 and variance t minus s. If you have non-overlapping in time interval, let's say r less than s less than t, okay, then wt minus ws is independent of ws minus wr. This is true for any rst. Okay, so first of all, right, w of t or w sub t, okay, this is the same notation, is a continuous time process. What that means is I have a time interval in my mind, 0 to big T. This little t can be any value in between, okay? In contrast to discrete, right? Discrete random variables means that I can only take t equal to 0, t equal to 1, t equal to 2, etc., right? Here, t can take on any value, right, in this time interval. So it's a continuous time process that follows these three laws. Okay, if it's the first time you see these three rules, then it may look a little bit strange, but we'll unravel them and we'll try to help you understand what it means. Okay. So any questions so far about this? Okay. So let me tell you, right, how the Brownian motion fit into the model, and then we'll look at the math. The Brownian motion, you can look at it as the building block of the stock price, okay, under Black-Scholes model. Brownian motion is the building block of S and its return in the in the Black-Scholes model in the following way. First of all, ST is S0 e to the, let me do mu, okay? This is the physical model. We mentioned that before, right? So WT enters here, right? And all the other terms are constant, but they're deterministic. So this is WT. So the WT here is the only one that gives ST is randomness. 2, if you want to talk about the returns, right? What is return in continuous time context? So return, right? Returns has this point of view. So returns in continuous time context, right? Returns over the time interval. Let's say t and t plus dt. All right. So dt, you can think of it as a very small time. Very, very small. Then the return, right, is going to be, if you look at percentage return, is s plus dt, right, over st, okay? And of course, there's a 1 over dt, right, like this. Sorry, keep forgetting. Minus st, like this, right? The difference in the stock price divided by the initial stock price, and then rescale, normalize by the time interval, by the length of time. How does this enter? Well, so first a notation. When we do this, okay, this is nothing but the difference in the stock price. We will denote that by dst. D stands for difference, right? I believe that you have seen the delta notation. You have delta sk is sk plus 1 minus sk. Maybe in numerical or in other contexts. So this is nothing but the continuous version of that, right? Instead of delta, we have d, right? Instead of k plus 1, we have t plus dt. Instead of k, we have st. Okay. So without explaining much, okay, we'll get to this later. And the point is stochastic calculus, okay, will tell you that dst in this case is mu st dt plus sigma st dwt. Okay, so that's the thing. So the percentage return, if you will, right? So ignoring this part right here, will be the change in stock price divided by the stock price, right? Will be mu dt plus sigma dwt. So dwt, taking on the clue of this, will be a change in the Brownian motion. Okay. dt here, of course, is the length of the overlapping time. All right. So we'll discuss that. The log return also has its own version. So the log return, right, is going to be log, right, of st plus dt over st, right? But notice this is going to be log of st plus dt minus log of st. But this is nothing but the difference in log price. By log price, I mean log of the price, right? So again, following the denotation, what it means is it's going to be log of st, d log st. Okay, and again, for a reason why we haven't shown you, will be mu dt plus, sorry, is mu minus 1/2 sigma squared. Okay, so a lot of scary notation right now, maybe, but first, right, what am I introducing? I'm introducing this new object called a Brownian motion. For all intent and purposes, is a random variable. Okay, first and foremost, is a random variable. For a fixed t, is a random variable. Okay, is a normal random variable, right, with mean 0 and variance t. The difference is also a normal random variable. Okay, so whenever I do something like this, dwt, don't be super scared. It's roughly speaking a normal random variable with very small variance and mean 0. Okay, and so you see here, right, that so this is log return. Okay, what I want to, the only message I wanted to give you right now today is that the Brownian motion is the building block of the Black-Scholes model and its returns in the following ways. It enters into the Black-Scholes model very straightforwardly. If you want to talk about the returns, then the percentage return is connected with the change in Brownian motion. Okay. By the way, right, because the change has a normal distribution, this is exactly what I mean when I say the return, right, has a normal distribution. This is percentage return. The log return also has a normal distribution. But those of you who have sharp eyes might see the difference between this and this. And that's actually a rather deep fact that we will cover, right, in a future lecture about. So it explains by stochastic calculus, okay, which is a part that we must cover in the class. But the point is this, right, that remember I kind of told you, right, that there's a subtle difference of the returns. Here's a subtle difference. Log returns is always smaller than percentage return on a small time scale. So if you look at one identical stock price, okay, stock data, If you calculate its daily returns and its daily percentage return and daily log returns, you should see that the daily log return is smaller on average. Okay, so we will unravel this more, but I want you to be able to be comfortable with this language, know what it means and know how to manipulate it mathematically, programming wise, and of course, maybe with data. Any question? Clear, unclear, totally mysterious? Where am I at? Anyone?
I think it's good.
Oh, I know it's good for you because you've seen this before. So I'm asking for other people. Okay, cool, right? Because I want to make sure that the notation doesn't scare people off, all right? So let me say this, right? Maybe next class or even like maybe review or something, the review session, I'll ask you to play with the Brownian motion path a little bit. Because the first thing you want to do is to see that a Brownian motion path looks like this. Okay. So that's what we mean by WT, right? WT here is viewed as a function of T. As T progresses, it takes on different values. Okay. But the fact that it's random means what? The fact that it's random means that if you generate a path that looks like this, you generate another path, it looks like this. Okay, and you generate another path, it looks very different. But each of them is a Brownian motion path, right? Think of it like it's like a path of the binomial tree that you looked at before. But when we say a single value of WT, that what we mean, or let's say T0, okay? What we mean is we do a vertical slice. For example, right, WT0 right here is this, but WT0 here is this. And of course, sometimes WT0 must be negative, right? So if you fix a point in time, that guy right there is also a normal random variable. In other words, right, this may be a dramatic picture, but if you fix a point in time, then there is a normal curve for the WT0. You understand? Right, with mean at 0, but with variance T0. Okay. And same goes for the difference between the two W. Let's say here, right? So this is called the increment, right? Here, the increment is positive. Here, the increment is negative. Of course, it's random, right? But the increment itself also follows normal rule, okay? And so, right, a lot of this can be just bring out into view. And so in the last 1 minute or so, right? So the program that we will do, right, is going to be, of course, right, develop something called stochastic calculus to deal with how to deal with Brownian motion. Then we talk about Black-Scholes model, formula, Greeks, that kind of thing. Of course, this is pricing, right? Along with that, we will also not forget, right, the idea of simulation, right? Monte Carlo simulation, right? Graphing stuff. Okay, so a lot of things. Okay, a lot of things. So I hope that, again, right, the level of abstraction, I will try to keep it, not high, but the breadth of knowledge I require from you, or the number of things I want you to try, will be a lot. Okay, again, just because I think you want to bring in all disciplines, right, when you study these things, so that you get a complete knowledge and you train yourself in a good manner. Okay, so that's that. I will kind of compose what for you to do on the review session. Hopefully something on simulation. Okay, I'll fix my program, post it, and post some kind of homework for you to do next week. Meanwhile, if there's any question, okay, feel free to send me an email. All right, or come to office hours. You can make an appointment too. I know in the afternoon here it's not good for you, but you know, if you want to meet in the morning here, meaning your evening, let me know. Okay, we can make an appointment. All right, everyone. Thanks for attending. I'll see you next time. All right, or at office.
Thank you very much, Professor.
Thank you. All right, see you. Thank you. Thank you.